I have a master's degree in robotics and computer vision, and now I am a second year PhD student in Innopolis University. Also, I have been like a senior software developer for 2 years. I have been working with like autonomous vehicles. Uh, I have been working with autonomous vehicles in the autonomous center in my university, and actually we are not about research only. We are taking like some projects from company. It's industrial projects. So we are developing like self-driving cars. We are developing self-driving trucks, even like self-selling boats, and that's what I'm going to show you like some of it today. So that's a brief about myself, and let's start. So here is the table of content. Today we have like the introduction, and then about like the autonomous vehicles and what's defined like an autonomous vehicle. And then we will talk about the sensors that is used for the autonomous vehicles. And then what is the modules, like the software modules that is used for such autonomous vehicles that can give us it like some perceptions, that can give it some controls, that can give it like some like we can say like make it turn into like somehow a human that can perceive the world and that can take a decision in order like to move freely in the world. And then what is the tools that is used that we like usually used in this field. Also we'll talk about the challenges that we face, and then we'll like summary everything and conclude everything. And you can while we are going, you can like ask questions. If there is something you don't understand, you can ask and I will answer you. So let's start. So what is autonomous vehicles? So like most of the people think that autonomous vehicles is self-driving cars only, but actually it's not. Like anything that can have like some level of autonomy, it can be described as autonomous vehicle. So like a truck can be autonomous vehicle, drone can be autonomous vehicle, tractor can be autonomous vehicle, and even a boat can be an autonomous vehicle. So like anything that can have like some sensors to perceive the world and can have like actuators to like go from a point to point or take some decision, that can be considered as autonomous vehicle. And actually like we have like 5 levels of autonomy: level 0 and level 5. So level 0 is non-autonomous at all, and level 5 is fully autonomous, and between them like there's level 1, 2, 3, 4 until we reach 5. So for example, level 1, like for a cruise control for a car, it's like just like a cruise control that can help you like keep the speed of the cars. This is like level 1. 2, it's some like assistance, it can assist you somehow in driving, but you still drive. 3 is when like you get your hand off the wheel and you help like the car, but it's still like the car itself can drive, but you can help it somehow. And then the level 4 is that your mind is off, or your mind is like you don't need like to think about a lot of stuff, but you need like to keep watching the surrounding. And level 5 is you don't need to be there at all. And actually like right now like there is a lot of efforts that we are trying to reach level 5, and even Tesla is trying, as you can see, but no one yet like could make it like a fully autonomous. Maybe like you can see sometimes, and even in my city here I can see like a robot that can go from place to another without the intervention of anyone, and even like a self-driving car. But it's still like in some environment, some small city for example, or some known city, but in like general it's not yet developed, because like they afraid of failure of system somehow, sometime, because like the safety needs to be ensured first before like deployed to a big city. So this is the introduction about autonomous vehicles. So now we will talk about the sensors. So, and sensors is like the human. So to perceive the environment, we need sensors. So like we have like the eye to see what is around us. We have like our ears to hear what is around us. So we can like deal with the environment and then take actions based on this. Like so our brain process these informations from the sensors, and then like it take like it gives the orders to our hands, which is actuators, to like perform some action to move from a place to another, and so on and so forth. So the autonomous vehicles need the same. It's need the sensors to do the same. So typical sensors used for autonomous vehicles is, as you can see, it's LiDAR, camera, radar, ultrasonic, a GPS, IMU, and like this is like, and even a wheel encoder. This is part of like what can be used. Like all of them can be used for autonomous vehicle, or some of them can be used with autonomous vehicles. So like, for example, Tesla doesn't use LiDAR. It uses like mainly camera and some other sensors, and that's it. So you can choose whatever you want based on your needs and what you want to do. But this is like the typical sensors that is used for the autonomous vehicles, and we will talk about them, uh, how the data looks like, and what is like the pros and cons for each sensor. So for example, here, like as you can see, this is the range for each sensor. So for example, for the LiDAR, it can give you like, or it can perceive 360-degree around the car. The range of the LiDAR is typically from 100 meters to 200 meters. 200 meters is like very long distance for the LiDAR. It's max, I believe. And normally, like the LiDAR operate from 50 meter to 150 meter. But it can perceive like 360 around 360-degree around the vehicle. For the radar it have like maybe small range, as you can see. So, but it have like a higher range, so it can give you like up to uh, maybe 500 meter or some sort. So the radar it have like a longer range than the LiDAR. The camera also like doesn't have a very field of view. It have maybe only 80-degree field of view, uh, and so on. So this is about them. So each one like have its like pros and cons, and we'll talk about this in more details. So let's go and talk about each sensor. So for the camera, so for the camera, for example, as you can see, so this is like a typical image, and we all know like how the camera like give us the data. It's just like composed of some pixels, and it can be like, for example, the camera can have like 1920 width multiplied by 1080 height, for example. So like I believe like all of us know how like the cameras work, so like no need to describe it in more details. But what about the LiDAR? So the LiDAR is light detection and ranging. So it's a sensor that fires a laser beams. So you can imagine that the LiDAR can have like maybe from 16 channel, 32 channel, 64 channel, and 128 channels. So how's like this? What is the meaning of these channels? So you can imagine that the channels are like a laser that is placed on the top of each other. So if we are saying 32 channels, so like we have like 32 lasers that are placed on the top of each other, and they have like an angle between each other. So what is the LiDAR doing? So the LiDAR is firing, for example, we are talking now about 32 channel LiDAR. So it fire a 32 laser beam, and then it move a little bit horizontally, and then it fires 32 and move a little bit, and fires 32 laser beam and move a little bit. So while it fires the laser beam, so it fires the laser beam, and you know, like the light speed is very high. So it fires the laser beam and it wait for its return back. And when it return back, it can, when it hit an object, it will return back. So it can calculate this time, and from this time, it can calculate like the distance between this laser beam fired and the object. And after this, you will have like an information about the X, Y, Z for this point, and even like the intensity that this point returned with. So this is how the LiDAR is work, and it will give you like a point cloud like this, and it can work like for 360 degree. And it's worth to mention that, for example, for the camera, it can work for with 60 frames per second. It can give you like 60 frame in 1 second or 30 frame in 1 second. It's so high, but for the LiDAR, it can only rotate for like a 360. Like it can only rotate 10 frames per second. So like this is like a physical limitation because the LiDAR is a mechanical sensor as well, and it's need to rotate. So for example, it's 532 and it move with a 0.004 degree and fire again and move and fire until it contain the 360 degree, and it rotate 10 times 360 degree. So it's only like 10 hertz or 10 frame per second. So it's slower than the camera, we can say this. And that's a drawback for the LiDAR maybe. Also, it's worth to mention that the LiDAR is more sparse. We will talk about this later. It's more sparse than the camera. As you can see here, there is, for the same frame, there is some gap between each fired ray and the other one. There is some gap, even though the camera didn't have like this fire gap. So for example, for the LiDAR, it can be 32 vertical for each frame. Here in the camera, it's 1080 pixel for this height. So the LiDAR like suffer from like sparse problem. The camera have like more dense or more dense photos or more dense images. So this is like about the LiDAR, and like here, as you can see, the data of the camera is pixels of red, green, blue channels. For the LiDAR, each point represents the X, Y, and Z, and the intensity, like like for example, for different materials, it can the intensity can like differ. For example, if it hit a solid car, it can have a higher intensity, but it hit like a leaf of a tree, it can have like a lower density. So like this information is also important, and actually like it's for different lidars, it can have like it can have a different fields or a more fields. So for example, it can have the ring. The ring is telling you like from which a laser this point is fired. For example, like the lowest laser is indexed with 0 ID. So like ring 0 is that fired from the lowest laser. The highest laser, for example, we have like 32 channel. So it's indexed from like 31 ID or 32 ID. So like it's just like saying to you like from which position this point that you are seeing is fired from. So this is for the camera and the lidar. Also, we have like other sensors as radar. So what is the difference between like radar and camera and lidar, for example? So radar is sending like some sort of a waves that have like a defined wavelengths, and when it hits some object that's moving with the speed. So for example, if this object is coming to you, then and this wave hit it, so it will contract and it will come back to you with a compression. So from this compression, you can like calculate like the speed of the vehicle at this position. And if it's going away from you, then this returned beam, it will be like more stretched. So like you can also calculate. So the radar can help us like in defining the speed of the around vehicles, can help us in prediction for like where this object is going. But the problem with the radar is that mostly it will need like the object to be moving. So like if a static object, it will be hard for the radar to detect it. And also the radar have like a small range of detection, which makes it harder like to detect it. So, and for the GPS, and we all know like the GPS. So the GPS can define like the position for the autonomous vehicles in the like in our world. Uh, however, like the GPS like have some drawbacks, but let's talk about like how the GPS working firstly. So the GPS firstly need to have like a coverage for the open sky, or like it's need like to see the sky. So for example, it needs to connect to satellites. So at least the GPS needs to connect to 3 or 4 satellites in order to be able to give you like accurate or at least like your coordinates. And the more satellites it's visible for the GPS, the more accurate it will be. And actually, like also, there is some ground station that the GPS needs to connect with, so it can correct the position for for your location or for your autonomous vehicle. The problem with the GPS is that, for example, if you are going under a bridge, you can lose the signal, or if you are going with for some area with a lot of buildings, you lose the signal as well. And if you lose the signal, then you will not know where you are and how like you would like continue like moving in your bus or something. And that's why you can't depend only on the GPS. You need to depend on other sensors in order like to overcome this problem. And here is the IMU. The IMU is one of the most important sensors as well. So the IMU, sometimes you can hear that this IMU have like 3 degree of freedom, 6 degree freedom, or 9 degree freedom. What does this mean? So firstly, let's say that the IMU is the inertial measurement unit. It stands for inertial measurement unit, and it can give you like your orientation. So the IMU, it can have like 3 sensors inside it. So the first sensor is the gyroscope. The gyroscope is responsible for giving you the orientation about your X, Y, and Z. So the orientation about the X is roll, orientation about Y is pitch, and orientation about Z is the yaw, or your heading. So this is the first sensor that is inside the IMU, which is the gyroscope. The second sensor, which will give us like 3 more degree of freedom, is the accelerometer, which can give us like linear acceleration. So it can give you like what is your acceleration in the X, what is your acceleration in the Y, and what is your acceleration in the Z. Also, it's worth to mention that if you have like the acceleration information, so it will be easier for you like to integrate it one time to get the velocity, and then you integrate it like another time to get the position, relative position. So for example, like after some time, uh, I like after some time when I integrate the acceleration and integrate it one more time, so I can know like my position after some time. And actually, this is so effective, so we can use this whenever like we lost the signal from the GPS. So for some time we can still continue with the IMU until we like have the signal again from the GPS. Also, there is another sensor in the IMU unit. So it's called magnetometer. So the magnetometer is like it can detect like the magnetic field from the earth. So like you know that the earth, it have like a magnetic field that goes from the south to the north, and this magnetometer is can feel like this magnetic field and can give you like where is like the gravity is towards right now, and this stuff. And this can help us like in defining the orientation and like the orientation of the vehicle itself. And this is information is very important. And like, you know, it depends also on the manufacturer of the IMU sensor. For different IMUs, so they use maybe the three units, which is the gyroscope, the accelerometer, and the magnetometer. They combine their data and they try to give you better estimation of your orientation, your acceleration, and velocity, and this stuff. It's so important. So, and the better they do this, the better is the IMU. There is okay. This is for the IMU, and the IMU also, like, let's talk about its cons. It have some cons about there is something called drift problem. Drift problem is something is when you like the orientation start accumulate, and you like no longer can detect where is your true position. It just start accumulate. This is like a common problem for the IMU. And the fusion between like the gyroscope, the accelerometer and magnetometer, it helps us like in reducing this problem. So this is for the IMU. And sometimes we do sensor fusion between sensors. A lot of time we do actually this. So why do we need sensor fusion? So we talked about that. For example, this is the camera, and here is the LiDAR, and each sensor of them have like its pros and cons. So for example, for the camera, it have like it's sensitive to illumination, and it can work bad when it's dark, for example. But for the LiDAR, it doesn't care about this. It will work morning as night. It just fire some lasers and it waits for its return, so it doesn't have a problem like this. And for the LiDAR, it have like this data density problem, and camera doesn't have this. So sometimes they need like, we need fusion to take the best from each one. So like they support each other. That's why we sometimes need fusion between sensors, and to get like a more accurate data and to perceive our world better. So it's the same as a human, what we do, but we don't see it, because like if you are using your eyes only, it will be hard for you to perceive the world. But if you use your ears only, it will be hard also to perceive the world. It's like when you have the two information, it helps you more. So and so on for all the sensors. So the modules. What is the modules or the software modules that we are using? So after we get the data from the sensors, and by the way, like getting the data from the sensor is not that easy part as we are talking. We have like a lot of difficulties in gathering the data. Like for example, you are taking the data from all the sensors, you are connecting it for your computers through Ethernet, and this flow of data can have sometimes, for example, like if the image is with very high resolution, it can like have a very big size, and it can like your Ethernet or your data transfer can overflow or something. So it's not that easy. You need to care about everything that is getting to your computer, and how to process it, and how to give like the commands to your actuators. So it's not that easy as we are talking. It's you will really face a lot of challenges in this part in gathering the data. And you need to firstly like configure your sensors well, and like configure like your camera, for example, to have like aspect ratios that that you need truly, and the resolution that you need. Because like, for example, one time we used like a very good camera. It's cost about $1,500, but it was like very hard to work with it with a very high resolution, and very hard to work with it with high frames per second. There is a limit. So like the Ethernet speed limit is about 100 megabits per second, and we have like 3 cameras, and it was like overflowing a lot. And also the LiDAR, the data from the LiDAR, it's sparse, but still like a lot of points that you need to deal with. So like, for example, the LiDAR can have 200,000 point, and 200,000 point, if you will deal with a lot of algorithms that will deal with this amount of data, it will be hard for maybe your computer to deal with. So like you are facing a lot of challenges in this part. So for the modules, so after you take the data from the sensors, and you will start to give it to your module. So we have like the perception module. This is where my expertise lie, and the SLAM module. And then after, like, we have the output from the perception and from the SLAM, we give it to the control module. And then the control module like will try to make a path planning for our vehicle, and then it will give like the commands for the actuators to move from a place to a place. So we'll talk about each module from the 3 modules, but it's worth to mention that the perception module and SLAM module, we can consider them as they are working in a parallel mode, but the control module is working in a sequential mode with both the perception and SLAM. So here is like the perception module. Like this image is really like looks not good for you. I wanted to make it like more real. So like I have get some data from my work. So yeah, this image is really like so confusing for you. And what is this? So this is the first thing that we need to do. So for example, we have like the LiDAR. We need to set a frame for it, like the X, Y, and Z frame. And we need to tell like our system where is our LiDAR is lying right now. And then we need to set where is our 3 cameras lying with respect to our LiDAR, and then where is our IMU is lying with respect to our LiDAR. So like we need to define where is each thing with respect to each other, or with respect to our LiDAR. This is the first thing. Why we are doing this? Because when we need to, for example, project the point cloud to the camera, we need to know where is like their respect to with each other, so we can like do the transformations. This is a very important step when you are dealing with mobile robots, autonomous vehicles, or any robotics application. And then you are trying to pass your information, whether it's camera or LiDAR, to your modules, your perception modules. So for example, here's we are passing the image through a neural network that make the segmentation for us. As you can see, like here it was for the boat, and it's segment the water, sky, the and even like the land. So, and even like if there is an object, it will also segment it. And here, as you can see, like we are using some YOLO to detect our objects. So like this is one of the first steps that we do after like getting the data. Here's for the LiDAR. We are trying to take the point cloud, make some modifications using like maybe the IMU to make the, because like when you are, for example, in a boat, the waves will make the boat tilt a lot, and this will make your point cloud fluctuate a lot. So you need like the IMU information about the orientation to correct your orientation, or fix your point cloud. And after you getting like the object of your point cloud, then you will start maybe here's your object from the point cloud. Maybe you will start like do the fusion between the camera and the lidar. So you will try to project the point cloud to the camera and try like to use this. So why you are detecting objects? What is the use of this? So we are trying to perceive the world around us. We need to like give information to the control module that there is an object here, there is an object here, some sort of things like this, so they can like make their planning and they can control their vehicle. So here is an example for the outputs that is come from the perception module. So like, for example, we have like this occupancy grid. And as you can see, like if the occupancy grid have like this black cells, it means that this cells is occupied with some obstacle and that your vehicle can't enter these cells. But if it have like some gray values as this, then it means that this is a free place that you can move freely on. And this is very important, and this is given to the control team, so they can like do their planning. They can do their global planning and local planning, and we will talk about this later. So for another module, so now we talked about like the perception module. Now we'll talk about the SLAM module, which is working in parallel. So what is the SLAM? I didn't find better than this link to explain like the SLAM module. So SLAM is stands for simultaneous localization and mapping. So what is simultaneous localization and mapping, which is SLAM? And it's a very big field. It's not like it's not an easy field. So here, what you are trying to do is that you are trying to mapping your surrounding area. You are trying to place, like register the point cloud together in their correct place and put it like in the world frame map. And at the same time, you are trying to localize yourself. Where are you like in this map, or where are you in like the global world? That's what SLAM is doing, like in a summary or an overview. As you can see here, like there's some robot that's keeps scanning the environment, and it's update its map, and at the same time you can see like it's track for the position where it is the position, and sometimes it's correct its position. So like this is a very important step for as the mobile robots in general and autonomous vehicles. So you need to know two information. The first one is to perceive the world, like you need to know where is the obstacles with respect to you. And second information, you need to know where are you right now. So this is the perception, what's the perception and SLAM is doing. And I can show you like some of the real sensors. As you can see here, like this is house look like the lidar, and there is a camera, and this is IMU. They have like some sort of IMU. Yeah, sorry, the IMU is on the camera. This is like their system. So they are trying to calibrate the sensors together. For example, like the camera with the lidar and with the IMU, and so they can start take the data. And they can register the point cloud, because like each point cloud you take is with respect to the lidar, but how this points is with respect to the world frame, or how we can like assign it to the world. So that's why like we need like the SLAM. There is a lot of techniques that is used for SLAM. There is algorithms that called Monte Carlo for that you can do SLAM with it, and there is this LeafSAM is one of the advanced techniques that is used recent years. just a paper published in 2021, if I remember well, and it shows like a very good results, and you can use it like to keep track of your vehicle, where it is, and if you lost signal from your GPS, you can keep tracking your vehicle. So that's for the slam. So then for the control module. So after we know where we are in the global world and we know what obstacles are around us. So imagine that we need to go from a point A to point B. So what are we doing? We have like a global path planner. So for example, the black one is the global path planning, and the vehicle is want to grow from here to here, but it faces some obstacle or it faces anything, so it need at some point to like make the local planner take a decision that no, this route or from this point to this point we can't move here, so like it need like maybe to shift or go somewhere else. It's like a human. So for example, you are going to your university from home to university. So you know like the global path planning. So you will follow this global path planning. But can you follow the same path every day? It will be impossible because like every day you perceive new obstacles in some place that you moved yesterday, but today there is an obstacle, there is a person that is moving, there is a car, there is anything. So like you will need to replan your path while you are moved. So that's why it's so important to have a global path planning, so our vehicle know like the map and where it's go from point a big points like from point A to point A or between two destinations, and the local planners that can adjust your path according to the obstacles in the environment. So that's for the control modules, and also it's worth to mention that it looks so easy, like you can here use maybe a star planning algorithm or any sort of algorithm, but there is another challenge that can face you here. So like, for example, the algorithm can give you like maybe a path that is near the edge, but your robot dimensions is need to be taken into consideration. So for example, like if the path was going here, that means if you follow this path, then your car will be out of the road. And that's thing you need to keep in mind. So you need to take like the consideration of your vehicle's dimension. You need to take the consideration of like the steering. For example, like I can't make like a sharp turns for the vehicle. It will be hard to follow, like the vehicles can't make this sharp turns, for example. So like you need to smooth your path as far as possible. And this like will require a lot of algorithms and a lot of work to do it. So it's not that easy like to go or to plan like from point A to point B. You need to take a lot of considerations while you are doing this. And this is like for the control module. And last thing, so before we continue for other stuff, which is the tools that you need to use, I want to mention that, for example, we have like, you can use a lot of modules for perception. You can use a lot of modules for SLAM or control. So for example, I have like the best perception module or the best detection neural network in ever, and it can give like a 100% accuracy for the objects around it. But this neural network, for example, works like it's slow. For example, it can give you like the output in maybe 5 or 10 seconds. So it will be impossible to use it in your mobile robot. Why? Yeah, it's very accurate, but if it take 5 seconds or 10 seconds, then it's like danger to use it, because like you will wait for the output from the neural network while you didn't take a decision in this time frame, which means that you can probably like hit some obstacle or hit some human. So like even if this module is very good, but you need like to take into consideration the speed of this module. So whenever we develop a new module for our perception pipeline or our SLAM or our control, we need to test like how much it take. Is it worth to use it or not? So for example, we can compromise with a lower performance module for the sake of speed. That's like a very important term in robotics, which is real time. Does this module work in real time? You can see a lot of benchmarks, models, neural network models, but we can't use it because like it will not work in real time. So it's a compromise always. So whenever you are developing algorithm, module, anything, you will need to care about how long does it take until it give me like an output. So this is for the modules and sequence fit, and then for the tools that we are using. So what we are usually to develop. So for the OS, we usually use like Linux. Some people, I hear that some people use Windows or Mac, but yeah, you can, I believe, but it will be hard. It will be harder. And it's better if you are using Linux. Most of the solutions on the internet, if you stuck in at some problem, you will find like probably will be Linux only. But you can still use Windows or anything. But it's better. Like it's mainly for robotics. And actually, like Docker have made everything easy right now, which can make you like work with Windows. But even like on Linux, we are working with Docker. So Docker is like this is I'm talking about like the tools that you maybe you will need to learn or you will work with if you decided like to go to this area, and how we are doing like the work. The Docker will make it easier between you and your team to work like the same environment with the same dependencies, because like in the past, it was hard to keep all the team developing with the same dependencies. Sometimes you install a dependency and you forgot, or sometimes you install a dependency and it make a conflict with other dependency, and then you will need to reinstall your OS or something. So like the Docker make everything about this easier. Also, you will need like maybe to learn the robot operating system, which is ROS. The robot operating system actually is some frameworks that can give you like a communication between your modules. For example, like you need your modules to work in a parallel mode, and you need like some sort of message they can communicate with, and some sort of a visualizer that can show this kind of messages. So like the ROS can help you in this area. It's just like a framework that like you can use to communicate between your modules, or you can visualize your output from your modules. About the languages that we are using C++ and Python. They are the main languages for robotics. And I believe like all of you know that Python is better in development and easier, can have like a fewer lines of code, a lot of libraries, but it can be slower than C++. So the preferred actual language for the robotics or mobile robots is C++. It's faster. It can give you like the response in least time. The Python you can only use maybe for development, for quick development, to test your idea, or at some parts of your project you will need Python. But mainly when you are at the deployment part, you are like now to make your system industrial, it's better to turn it into C++. However, I saw some people that develop their systems fully with Python, but it will not be easy. I believe. So, but probably this is the main languages that you can use for programming autonomous vehicles. Also, some of the libraries that you will face is, for example, PCL. This is mainly you will use PCL for like handling point cloud. So when you receive a point cloud, you will need like to do some operation for it, like pre-processing. So like, for example, that you get from your LiDAR maybe for 100,000 points. This is too much to handle. So what you need to do is maybe reduce this amount of points, or maybe like you need to cluster this point cloud. Like for example, the near the point are to each other, we need like to cluster them together to form like a one object. All of these operations you will it's easier to use PCL for it, and PCL mainly for C++. There is also another library called Open3D for point cloud that come from the LiDAR. There is OpenCV that you will use when you work with camera images and anything like that related to camera, I believe. TensorFlow, PyTorch when you are training your models or doing like kind of this stuff. So this is for the tools that you will probably be using in this field. And even like there is in the recent years, there is a trend that most of the people going towards CUDA. CUDA is like a C language, we can say, programming language that can parallelize your code or parallelize your operations to make it faster. What we do with this, so like NVIDIA is providing the CUDA, and they are trying to transfer, like most of the process is done on the processor, but some of the process we need like to move to the GPU, and probably it will need to be NVIDIA only. And you like, for example, if you know, like all the programming languages are sequential, but for CUDA it can like make everything parallel. So for example, you have like 200,000 point of the point from the point cloud, and you will need to look, for example, for this point cloud one by one. So you will need to wait like until the 2000 operation for this point cloud is finished. But for CUDA, for example, you can like transform all of this point cloud to the GPU, and we can like separate these points on the number of cores or we have on this CUDA, and then we can do one operation, like all of them are parallel. We take the output and then we move again. So like instead of looping 200,000 times, we only loop like one time. It's easier and more efficient, and actually like that's what we are doing in right now. And yeah, actually it's help a lot, and it's make your code faster and your pipeline faster, and it help you like to go more towards uh, uh, can you hear me? Please, if you can hear me, can you reply? Hello? Is anyone can hear me? Guys, hello? Can you hear me? Okay. Because like someone like couldn't hear, so like I thought like there's a problem with my connection. Okay. So this is like the tools that you can use probably in while developing. So let me show you like maybe some real world applications before we go to the conclusion. So here's like some videos. So uh, you don't need like to have like A mobile robot for sure. Like you can use like some sort of simulator. So for example, like this is when I was in my bachelor, I was just doing this kind of stuff. It was like using simulator because I didn't have like hardware back then, and it was small mobile robots. I was trying to map the area around me, use some kind of tools and algorithms. This is like what I told you about ROS. This is ROS. This is the visualizer for ROS. And this is like the simulator. It's called Gazebo. And here I was using like some libraries and tools like MoveIt, C++ code, and Python and stuff like this. And I was like, this was a small project that is going from one place to another, and some sort of. So at first, like the robot is move around, try to figure out the environment around it and save this map for later. Uh, and try meanwhile to avoid the obstacles. So this is like, as I told you like before, this is like called SLAM, simultaneous localization and mapping. And then second part here, the robot was trying to localize itself. I hope you can see. So for example, like here, it was incorrect localization, but it was trying to use its algorithms to try to figure out where it is. So for example, it is here, but on this map, it shows that he is here, which is a wrong localization. So like it uses a lot of algorithms while it's moved to try to figure out where it is, because like as you can see, it can see like these objects and it's drawn here, but it's wrongly drawn here. It should be like drawn here. So until it finds out where it is after some trials, now it's localized itself correctly. As you can see, like now it's here and it's the same at the same position. So like that's like kind of algorithm that is doing this heavy task. And for the real world applications, so here is like was a data that we were taking from the river. So here was we on a boat and we have like our system on the boat, like 3 cameras, for example, and our lidar, and like the boat have like some rebels behind it, and like here is how like the data looks like. Uh, Also the same, and here is like some boats that is going near to us, and how like these waves are appear in our lidar, and we need like to remove this for later, because like we need only like to detect the objects. Here is like, because the boat is fluctuating like this, so you can imagine this like that the lidar is fixed, and the world is rotating around it, because the visualizer will not understand that the visualizer is the one who is rotating. Like the data is come with respect to the lidar, so everything is with respect to the lidar. Okay. So this is like also from the problems for this boat, and we need to fix with the IMU. For example, like when the boat is tilting, so the IMU is tilting as well, and that's we use this information to correct the point cloud or to make the point cloud more stable. And then when we make like the point cloud stable, as you can see, like the red one is stable and the green one is moving around because like the fluctuation of the boat. And after we use like the IMU, we like reach it this red one, which is more stable. So like it's like the red one is stabilized, but the green one is moving back and like up and down. and so on. Like this is like some of our work, and sure, before like we start anything, like we need to calibrate our sensors. There is where we calibrate our sensor. We use, like, as you can see, like this A4 chessboard. It's for the camera and for the LiDAR. It's not A4, sorry, it's A1 size chessboard. You can calibrate the camera with A4 size chessboard, but for the LiDAR, it's hard to detect A1 chessboard. It's hard to, sorry, to take like small A4 chessboard. So we use A1 chessboard to calibrate even between the camera and the LiDAR. This is like one of our calibrations, and then we project to the point cloud on the image to see if it's on the same spots, correct spots, then we did the calibration right. And this is like a typical of what you will be doing if you want like to go into robotics. And this is some of the modules that the detection from the point cloud. So for example, you give it like the point cloud like this neural network, and it give you like a bounding boxes like this, and another neural network that you give it a point cloud, a whole point cloud like this, and it give you like the objects colored, like only the points for the objects around you. And this is helpful when you are trying to map the objects surround you. So conclusion, so we talked about like autonomous vehicles and what define autonomous vehicles. We talked about the sensors and what like can give like the vehicle a level of autonomy, and what kind of sensors can a vehicle use. It can use some of them or it can use all of them. It depends on your application, and the modules and the sequence of our modules, and until like from like getting the sensors data until it gives like the output to the actuators, and it can move like safely in the environment, and the tools that you can use if you want to go more deep into this area. So that's it. Thank you for your listening, and if you have like any questions, I would be happy to answer them. Thank you.
If you have a question, you can use the hand reaction to raise a question or leave a comment in the chat. So let's wait 1 minute to see if anyone, let's see, Zakaria Abdi wants to participate. Let's see what they have to say.
Sure, go, Zakaria. Hello?
I'm asking to unmute them, but
Zakaria,
you
if
can
you can hear me,
also
you can
write your
ask.
question in the chat. Do anyone else have a question in the meantime? Zakaria, are you there?
Okay, now you hear me now?
Yes, we can hear you
now
now.
we can hear you.
Yes. I have two questions. One is that thank you very much for your presentation. It's very delicious and very complicated as well.
Thank you.
This electronic engineering. You said C++ is more versatile than Python.
Yes.
And as we know, in practical terms, most of the people now are tuned into Python. How do you
Yes.
differentiate? I mean, C++ looks like an old type of computer language, or what do you call software.
Okay, I will. Okay, so what is the difference between C++ and Python? So
I
like,
mean, which one is more versatile? What we know is that Python is more versatile, more flexible than the C++. And you said
yes.
it's C++ is more used than C
No, I said that
than Python.
exactly what I said, that Python is easier in the development. It's, as you can as you said, like it's more versatile. You can develop with it faster. It have like more libraries and like, yeah, it's, and like a lot of people are using it right now, and it's easier even. C++ is harder, but you know, like when you the compiler, when your compiler is transferring the code into like a machine level code, it make it faster. The Python, like, we can't say like it's a higher level language. The C++ can like deal with a more low level control and this stuff, which make it easier or faster in term for the machine. So like it's not me, like you can even test like the same functionality with Python and C++. The C++ will be much faster than the Python. We usually like don't use Python actually. Like if we will use Python, it will be only for development, and then we turn everything into C++. I don't know like what is your background, but if, for example, like for example, like you know, like the embedded software engineering, they are trying even to enhance everything. They mainly use like C++ or C, even like to make everything faster, to make like the low level control for the cars, or for even like the small system, like your mirror, everything, like they're trying to make it faster. So in terms of speed, C++ wins. And even though like the Python have like in recent years uh, more development towards making it fast, or making it like access maybe like GPU, and trying to make it like C++ to transform it into like a machine language, so like it's faster, and there's many tries to do this. And as I told you, like there's some people that depends mainly on Python, but still, like if you will work with this or you will deploy your system, it's better to use C++.
Thank you very much. My other question is, I'm an agricultural engineer by profession. My first degree was that, and I work on agriculture, on what we call remote sensing. Sometimes when you have a say, for example, a large pest of locust attacking farms and grazing areas, we use what we call remote sensing from the satellites.
Okay.
Now, what we have a problem with geostationary satellites in terms of point blank. The other type is more clear and more, though it's more difficult. Which one you prefer to use for example, in a wide area exposure for the two types of the satellites?
It's two different GPS, you mean?
Yes.
So no, actually, like so like I'm not expert in this area so much. So like, for example, like I don't know like if this GPS is better than this. Maybe I will need to read like the user manual for it. But like usually I don't know like this kind of information. I just like have the GPS. I may read like the user manual of the GPS that I have and try to get the data, and that's it. And maybe like knowing how accurate this GPS was compared to others,
Yeah.
and this kind of information. So like you need like to read the user manual for each GPS, because like it's different. Like each one is different, and there is a lot of factors that like can make like your decision. So like for me, like I don't have like an answer to this question,
Okay. Thank you very
but
much.
you will need like to maybe read the user manual for each
Thank you
one.
so much, Mr. Mohammed. Thank you. Thank you, Professor.
Uh,
Thank you very much, Engineer. Thank you.
so
Thank
so
you.
so Bernard, you can have like you can go with your question.
Thank you so much, Mohamed. How are you?
I'm good. What about you?
I'm fine. I'm calling from Kenya. The question yesterday we had a class about languages, natural and artificial languages. We realized that Python has become the second the second used language in the world right now after English. What can you comment about that? Or why? Why do you think that one is the case?
For Python, like because it's used by a lot of fields, not only autonomous vehicles, for example, like it's used by web developers, it's used by computer vision engineers, it's used by even like programmers or in competitive programming, like a lot of people are using Python. The Python organization itself, like it's pushing towards adding like a lot of features, like enhancing the language itself, and there is a lot of contributors for Python, and the Python itself is like easy to learn. So that's why like the Python is becoming more popular with years.
Thank you. Thank you so
Okay.
much.
So anyone have question?
Question. Yes, we have a question from Elday. Let's make that the last question for today.
Okay. So Tayyip, you can ask if you can hear me.
Yes, I can hear you. Okay, thank you very much for the interesting lecture. In fact, my question is actually related to the autonomous vehicle. This autonomous vehicle, in fact, most of them are, as per my knowledge, most of them are just electric vehicles. In fact, any
Just
other
what?
electric, mostly I think electric vehicles.
Okay.
So what is the reason behind that, in fact? So there is any issue with the fossil fuels, if you use fossil fuel, or it's related to some sustainability and all?
Not all of them are electric. Like, for example, in my city, like there's self-driving cars and they are not electric. They are with like engine, normal engine, not electric engine, not electric motor. So not all of them, and there is matter of fact, like it doesn't matter a lot. It's just like the normal differences between electric vehicles and like gasoline vehicles or any kind of other vehicles. So like there is no different actually. Like the actuator itself is different. Like here is like it need gasoline in order to work. Here is it's need electric in order to work. So like there is not this much difference between them. You can find this and you can find this. The only thing that matters what sensors you are using on your vehicle, your computer. So like you can, for example, use a small Jetson, or you can use like a very powerful computer. This will matter too. But this is only the things that will matter. The quality of your sensors, the modules that you put in your system, how powerful is your computer, and the actuator, like the motor, maybe it's small motors that can control the wheel or anything. So that's what it will matter actually.
So just as a confirmation, there is, so we can use any type of fuel other than the batteries, I mean the electric batteries, which you
Yes.
normally use in the electric vehicles as environmental friendly, you can say.
Yes, we can use like, for example, like it can be like a Tesla, or it can be like a normal vehicle that you equipped it with some equipment, sensors and computers and this stuff, and maybe like some motors that can drive the wheel, and it will be autonomous. So you can make anything.
Okay. Okay, there is one more question, what is the risks involved while using these autonomous vehicles, in fact. I think it is not, now it is not spread more in the world. Maybe, as per my humble knowledge, I think there is a risk involved while using these vehicles in these roads, this kind of roads, in fact, or there is some specific roads should be designed to use these kinds of vehicles, or in the normal road also with other vehicles, we will be able to drive.
So I have a lot of vehicles that are moving in the street freely, but the risk is that you are talking about is related to the safety. The governments require a very high safety level because, like, it's the autonomous vehicles is still like any other computer system in the world that can fail at some time. Any other computer system in the world can fail at some time. It can lag, it can have a bug, it can uh, like be hacked from someone. So just this, but if, for example, like if I hacked your computer, or if someone like hacked your computer, or if your mobile like have a bug or so, like it will not affect somebody life. It's okay. You can like replace it, you can fix it. But if a vehicle like have a bug, have been hacked, have like any kind of issue, how much it's simple, it can like be danger like to some one life. It can like make some accident or something. So that's why like the governments maybe like have some restrictions on the vehicles, and that's why like it's just like being tested for some in some like maybe like safe areas, we can say, which have like no like or minimal interaction with humans. That's why like they are not spared yet. But the more safety it's added to these cars in like maybe emergency situations, the more situations you are handling, the safer it will be, and maybe like the more it will be in the future.
Thank you.
Welcome. So it
Question?
was nice to meet you. So if anyone have like another question, we can like